Thank you.
It's okay, Lisa will probably just switch off my screen so you can't see my face. Just listen in the background.
Yeah, maybe like if you put it like that.
I can't make clothes, can you? I'll do that for the intro, and then once we get to the...
Somebody else joined the Zoom.
Yeah, maybe if one of
like
those.
this.
Yeah.
Okay, it's not the full screen. See, it's open.
If one of them join the link, maybe that's a good idea.
So if I share the Zoom
try?
link with you guys, Zoom as well, right?
Yeah. Oh, I didn't know. Like just have to make
No, just check it out.
Yeah. Is emailing you guys the link.
Okay. Yours is better. Yeah, it's a kind of Zoom. Yeah. Zoom. Maybe just briefly see some. I don't know. Is the photo? You want it forward? I think it was. This way? This way. Okay, that's it. I mean, it should be a little bit like this. Okay. Okay, like this. That you see full screen.
Hi, good morning, everybody. So I'm Adam Egebrecht from Washington University, School of Medicine in St. Louis. We're just going to wait a couple more minutes because maybe more people are as jet-lagged as I am and are slow to come in. Or it's just a intimate crowd, so that's cool too. So we'll wait about 5 more minutes and then we'll get started.
Every damn song I hear is
All right, well, good morning. Welcome to the Organization for Human Brain Mapping educational course on optical methods for reliable and high-fidelity human brain mapping. My name is Adam Megebrecht, again, from Washington University. If you guys have any questions, just raise your hands. We can have this be very conversational. We would do that if it's more than the small number. So don't be shy. We're all here together. I'm very, very excited to share the stage with my esteemed colleagues. So we're going to hear from Hamid Dehghani, Chiara Bulgarelli, Emma Spey, myself, Lisa Kobayashi Frisk via Zoom, as well as Dalin Yang. So there was a really nice, timely article that came out just a few days ago in PNAS called Functional Near-Infrared Spectroscopy Reveals Brain Activity on the Move. A nice little opinion piece, so I urge you to just go and check it out. It's just a couple of pages, but it reinforces that mapping a brain function with positron emission tomography and functional magnetic resonance imaging have really revolutionized our understanding of brain function and organization. Since the mid-'80s with PET, since the early to mid-'90s with fMRI. But for those of you familiar with those technologies, the more traditional technologies are rather limited in applications that require portability, point-of-care assessments, or ecologically valid naturalistic environments, such as direct within-room social interaction and communication. Like if you wanted to do a study on the brain function underlying me fumbling through this, or you sitting in this talk, you can imagine a world where we have wireless versions of this cap. So this is just an example of some work that our friend David Boas is doing formerly at MGH and now at Boston University. This is a multimodal system. Let's see if I can do this without blowing the video out. There we go. So this is a multimodal cap that they're developing that has both fNIRS as well as EEG leads, as well as Tobii eye tracking glasses to be able to look at, to be able to record where people are looking in the visual scene as they just walk around Boston or the university, as well as getting fNIRS and EEG recordings, high bandwidth recordings from all over the head to try to really break through with multi-dimensional recordings about what's going on in the brain, how is it related to behavior, how is it related to eye tracking, etc. And so again, this is just the kind of thing that you just simply cannot do with magnets, even with the really cool low field stuff that's coming out of MGH now. Here's another example of an infant in the Gambia, and Chiara, I believe, is going to talk more about this, an example of an fNIRS cap that's used in the BRIGHT study. And so it's very exciting to be able to go into very low resource settings and go into ages where you can't get awake and engaged brain function easily, or even in an interpretable way with MRI. And so again, this is just an example of kind of old data out of our lab and Joe Culver's lab, just showing a sped up map of cerebral oxygenation with one of our earlier prototype systems, just showing the kind of data that you can get in a setting where people are sitting up awake in a system. And this can be extended further, or is being extended further into virtual reality contexts where kids can explore a free, open environment, or little kids can play interactively with their parent and again be wearing fNIRS and even EEG multimodal arrays to get a sense of what's really going on with their brain function during very ecologically valid settings. This is an example of one of my twins in a system that we're developing or have developed at WashU that she wears while she's watching Star Wars or Moana, etc. Again, all this fiber-based stuff is really just kind of a step in the road on the way to wearing a very lightweight, baseball cap type of technology that still gives us the high-fidelity imaging. And this is another example of a cap out of our lab where we're taking data throughout cardiopulmonary bypass surgery to be able to get fMRI comparable image quality just in the outer inch of the cortex, but luckily there's a lot of neuroscientifically and clinically relevant information going on out there. So this course is going to provide an overview of optical system strategies and processing approaches for using NIRS and more generally diffuse optical methods for mapping brain function in humans. By the end of the course, you'll be able to evaluate and differentiate the landscape of common methods and tools used for optical neuroimaging. You'll be able to explain how to use previous neuroimaging studies from either NIRS or fMRI, just like the fMRI community does. For example, how to generate regions of interest when planning a new study, or how to interpret novel results from either NIRS or fMRI, and how to incorporate them with tools like NeuroDot, NearFast, Homer, and other common tools within our community, and again, in the fMRI community. And if you engage in the hands-on tutorials, you'll be able to perform a range of modeling and analysis using open source tools in Python or MATLAB, as well as cloud-based container resources using XNAP. So again, Hamid's going to talk about the physics of light and tissue interaction. Chiara will talk about data collection and quality control over a variety of applications. Emma will talk about some data pre-processing and temporal analyses and incorporate some hands-on tutorials with pre-processing and with the cloud-based processing as well. I'll talk about tomographic reconstruction and a little bit more about the tutorials for light modeling and image reconstruction. Lisa's going to come in from ICFO in Spain and talk about some very exciting new developments with diffuse correlation spectroscopy for actually measuring blood flow, similar to what you can do with ASL, but in a very different way. And then Dalin Yang is going to talk about machine learning considerations with fNIRS data. So for those of you interested, I don't know if that link is really dark, but if you go basically to NITRC /NeuroDot and then click on the GitHub link, you can download the NeuroDot toolbox if you like, and inside of that toolbox are a variety of tutorials that you can go through in your own time, or you can go through while you're listening to us talk and the HDMI leave. But basically there are PowerPoints along with scripts in MATLAB that you can walk through to learn any number of the stages of processing with our tools. Additionally, on the NITRC website for NeuroDot, there is a downloads link, and if you go there, there's a documented PDF preparation for pre-processing and data analysis workshop. If you click on that, it'll walk you through how to log in and create an account on XNAT, and then you can actually run some of the one of the containers that we've developed for this workshop. So you can process NIRS data on the cloud. And you know, this is the kind of thing that the fMRI community has really been working towards over the last number of years, and this is brand new for our optical imaging community. So we're really trying to push forward data standardization and processing standardization. So with all of that, again, if you have a question, just raise your hand or go to a mic and we can have it be as conversational as possible. So for now, I'm going to hand it to my friend Hamid, who's going to talk about some of the underlying physics.
Okay, good morning everyone. My name is Hamid Dehghani from the University of Birmingham, and what I thought I'd do very briefly this morning is just to give you some overview of the physics of how light interacts with tissue and what properties within that physical model it is that we use for parameter recovery and image reconstruction. So our internal learning outcome this morning is to establish the motivation behind using the infrared light for imaging biological tissue, establish how light and tissue interact in giving us that information, and how specifically we can use models, computational and analytical, to recover these parameters from these optical measurements. And lastly, I will very quickly walk you through the use of a model-based software called NearFast that allows us to actually play around with some of these parameter recovery algorithms as well. So the aim of near-infrared imaging and spectroscopy, often also referred to as diffuse optical imaging, is that what we want to do is recover images of tissue absorption and scattering, often scattering, using a set of measurements in the near-infrared, 650 to about 1,000 nanometers, but we want to do this using a very few a few measurements on the surface of a tissue. And the motivation behind that is that the optical coefficient, and mainly optical absorption, is directly related to the physiological state of tissue, namely oxy and deoxyhemoglobin, lipids, water, and perhaps cytochrome concentration as well. And this makes optical techniques very unique because near-infrared imaging becomes a functional imaging modality. It's an imaging modality from which we can actually get pathophysiological information rather than just structural information. The use of light in medicine is nothing new. We've all seen and used pulse oximeters, and the whole concept behind that is if I was to shine light through a tissue at a given red wavelength, as the volume of blood in tissue due to the cardiac pulse increases, the absorption increases, so we can actually measure the heartbeat using a pulse oximeter. But since we know the absorption of light at different wavelengths due to the oxygenation state of tissue, if I was to measure the same signal using two different colors of red, red and infrared, and using this relationship and the knowledge about the absorption of oxyhemoglobin, then I can actually calculate some form of oxygen saturation in tissue as well. So the use of light in medicine is not new, but it's how we use this information to get information from deep inside the body. So if we start thinking about light as particles or photons, there's a number of things happens when we inject light in tissue. Well, first of all, due to the refractive index mismatch, some light is reflected from the boundary, does not enter. Then some light actually travel through tissue. We have completely lost it now. I didn't do anything, man. Bear with us.
Yeah, forgive us, there's an issue with the HDMI cable on the system.
Oh, what you just did then did something. Just not right. It's bizarre because my laptop sees it, obviously. Is anybody upstairs that can come and help? Like left. We have help coming, which is great. Yeah, you tried it.
Yeah.
If anything can go nice to hold it up.
Yeah, this is true. Yash had the interesting idea that if they had Zoom up there, we could just screen share it.
Yeah.
I doubt that.
So I'm not going to run through the tutorial then, the hands-on thing, because I'm not there to.
Yeah, to click through it. That's
yeah.
fine.
Yeah.
I'll wait to do
But
it
I've got a
before we
link
can.
up there now that literally says that you can download it and play. So that's
Okay.
Yeah. It's the box rather than the wires, right? Where is she taking it to plug it in?
Hopefully this will just be another moment, everybody. Thank you for your patience.
Should have get through all faster. It's difficult to know if you're doing it's working or not because you haven't got anything plugged in, right?
Yeah, so I may have fixed it. Let me see.
Bless. She's probably, I don't know.
She may have taken control.
I don't understand what she's doing up there.
Good morning and welcome. We're dealing with some HDMI issues with the room, so we'll be back on in just a moment, so you know. Did that change based on me?
No. That was on you.
So she's doing something.
That's the power to it.
Yeah.
So all that does
Windows
is
restart.
converts HDMI to passive function by Ethernet, right?
Yes. And then the Ethernet goes into that red cable that you might know.
Oh, I see. Oh, that screen's back. See, why is she not even... Oh, wow. I was going to play with that extent. Container.
Sharon, is it possible to try the HDMI from this podium again?
So that works pretty well now. Okay, do you want me to bring my laptop back down again, maybe?
Maybe I fixed it? We could try.
It's not flickering there, is it?
Yeah. So for those of you that weren't here the first time when we talked about this, we do have some online tools. If you want to do any of the learning resources, the interactive resources, if you go to nitrc/neurodot, you can go to the GitHub link for Neurodot on the left-hand side and download the toolbox. It's either used during today or for offline later. In the toolbox, there are MATLAB scripts and tutorials that walk you through multiple data processing pipelines for pre-processing, image reconstruction, post-processing, et cetera. And then there's also on the NITRC link this PDF preparation for pre-processing and data analysis workshop that will walk you through signing into XNAT, making a link on XNAT and getting an account there so you can run some containerized processing pipelines that we've set up for this. And we're developing more containers for standardized processing workflows that you can change parameters and change settings so you can do cloud-based computing supported by XNAT. So we're going to walk through both of those things later on in the workshop if you want to do that while we sort out the connectivity issues that are happening in the AV. Hopefully, we'll be back up and running in just a moment. Thank you again for your patience. Hamid, if you can hear me, we could put yours on my computer since my computer's working, or at least the HDMI connection on my computer's working right now. Of course, maybe this is showing that it's not. This highlights the importance of troubleshooting, which is exciting.
Fantastic.
Do you want to try to run from down here?
No, I'm just going to use what's on there already. So let's. Cool. All right, we're gonna go forward, and what we were talking about before is light tissue interaction. When you're exciting tissue with light, a number of different mechanisms can happen. One is that some of the light will be reflected back on the surface. This is simply due to Snell's law and the refractive index mismatch between air and tissue. Some light will travel through tissue, and as it travels, it will be absorbed and it will lose its energy. But tissue is scattering, so also, but light is not high energy enough to cause ionization, so you have elastic scattering. So light will eventually scatter and get absorbed at small amounts and eventually exit tissue. These two mechanisms, absorption and scatter, is what we're concerned with in near-infrared imaging and spectroscopy. There are other interactions, namely Raman scattering and fluorescence, which we're not going to talk about, but it's important to be aware that these things can happen too. So, optical attenuation in near-infrared, we are concerned with absorption and tissue scattering. So, what is functional near-infrared spectroscopy in a nutshell? Well, in a nutshell, what we're trying to do is we're trying to measure optical absorption at multiple wavelengths, typically at least 2 at either side of the isobaric point where the absorption of oxy and deoxyhemoglobin crosses over. And if we can measure the absorption at least 2 wavelengths, then we should be able to recover optical related parameters, and namely oxy and deoxyhemoglobin and their concentration of. So when we actually use multiple wavelength measurements, we are able to recover optical parameters of absorbing molecules, oxy and deoxyhemoglobin, water, fat, cytochrome C. But also, if we have the mechanisms to measure the scattering of tissue, it's possible to use what we call MES theory, where we are assuming that all particles in tissue are spherical and elastic, and we can model for the density and size of particles in tissue that will give us information, for example, collagen and mitochondria as well. So this is not often very seen, but we are mostly concerned with absorbing only related changes. So how do we go about measuring, once we've measured the optical attenuation at multiple wavelengths, to recovering this chromophore concentration? So on the top, on the right-hand side, I've given you all the abbreviation of the variables that we are using. So typically what we are doing is we are measuring the optical signal, the change in optical signal as a function of time at different wavelengths. And what we're trying to do is recover absorption and or scatter using some form of a model, and that's what we call G. And once we actually recover the absorption at multiple wavelengths, then we can combine them using Beer's law to get concentration of oxy and deoxyhemoglobin. So we go from a measured data at multiple wavelengths to recovering absorption, and from absorption we go to recovering to change the concentration of molecules. But the important thing is this mapping function, this model on what we use for the recovery of absorption from the data. The problem is that tissue is scattering. So we've all seen that if we take a cuvette of water, we shine light through it. If there is no scattering within that medium, the amount of light comes out. Since we know the path length of light, which is literally the thickness of the cuvette, we can recover the attenuation and therefore the concentration of the molecules within that cuvette. But as soon as we add scattering, in this case just 2 drops of milk to the cuvette, then the whole the problem is no longer a light going in a straight line. Light is scattered, so therefore the light that we measure, we have no idea the path that the light has taken. So therefore scattering and absorption will give us a problem in recovering this absorption of molecules accurately. So near-infrared in biological tissue, light becomes diffuse, and that's why we often call it diffuse optical tomography. So how do we overcome potentially in this scatter-related changes, or what I should say, what are the typical ways of we measure light transmission in tissue? The most common methodology is what we call continuous wave, where we shine light at the surface of tissue whose amplitude is constant, and what we measure at the detector is just a reduced amplitude of the light coming out because some light has been absorbed. But since we are not changing the intensity of the excitation and we are just measuring the amount of light coming out, we have no information about how long it's taken for the light to travel, so therefore we have really no information about tissue scattering using continuous wave measurements. Alternatively, what we can do is we can actually use pulses of light, typically in the 10 to hundreds of picoseconds. We pulse light into tissue, and light travels through tissue, and the detector, we use a photon counting system, and we measure how many photons come out as a function of time. And if we do this multiple times, we can build up a histogram of what we call the temporal point spread function. And now, since I know how many photons come out as a function of time, I can recover both absorption and scatter. So that is called time resolved. And we could also do this in frequency domain. So if I take my amplitude I've got in CW and modulate its amplitude at a given frequency, typically in hundreds of megahertz, and I can look at the light coming out at the detector, I am looking at the same modulation frequency, so I see a reduction in amplitude due to absorption, but also I will have a phase shift that will tell me something about the average time for the photons to propagate through tissue. So frequency domain and time resolved, they provide you both information about tissue absorption and scattering. Where continuous wave, we have to make assumptions about tissue scattering because we don't have that information in our measurements. Another related technique that we're going to learn about later on is called diffuse correlation spectroscopy. So if I was to take a laser light source, typically with a long coherent, which has a long coherence, and I was to shine that through a tissue, we can see that if we have movements within this tissue, for example, blood flow, and I was to look at the surface fluence, I will get speckle patterns. Simply, and the speckle patterns will be correlated to the movement of particles within that tissue. So if I was to look at one point in the measurement and I was to correlate the fluctuation, then I will see that this correlation will change whether the flow in tissue is slow or fast. So using diffuse correlation spectroscopy, we are able to also pull out an index for blood flow that will initially tell us how things are flowing within that tissue. And Lisa, we're going to be talking about how we utilize this information for brain imaging later on as well. So how do we go about in using these models to actually fit the measured data to absorption and scatter? Well, if I was to take a piece of tissue and assume that it's semi-infinite, I can literally use the Beer-Lambert's law. So shining light into tissue, I know that the amount of light traveling through a tissue will be exponential given the distance away from that source and the overall attenuation that incorporates both absorption and scatter. So as I actually start moving away from that source, then my measurements as a function of distance will be exponentially decaying. So this is the log intensity of light measured, and this is the function of distance away from the source. So since we are using Beer-Lambert's law, then I can turn around and say my attenuation is the negative of the ratio of the amount of light coming out with respect to the light going in. So that attenuation is often called optical density, and therefore the gradient will be proportional to the overall attenuation. So if I was to then go and plot my optical density as a function of distance, that the gradient of this line here will be proportional to my effective attenuation of light in tissue. But can we actually do quantitative spectroscopy? And the argument here is that for small changes, yes, we can. So if I was to actually start looking at what I've just shown you, attenuation as a function of now absorption, not distance, they've got two different lines just to show you that attenuation is affected for different scattering values. And the argument here is, again, these equations that will just demonstrate that the gradient is proportional to the effective attenuation. And we know that it's not linear in distance or mu A or mu S. But however, if I was to look at one optical density as a function of absorption, and if I was to measure a relative change in attenuation, that means I'm monitoring tissue and I'm looking to see if light attenuation is changing by small amounts, that can be linearized to a small change in absorption. So that means even though this line is not linear, by looking at small changes, we are effectively linearizing this, and we can fit a straight line to that, which means that the rate of change of optical density is linear with respect to rate of change in absorption, which means that fNIRS can be used as a method to quantitatively assess the relative changes of tissue hemodynamics. There is also this additional, what we call a differential path length factor that we have to use simply because we are assuming something about tissue scatter, typically when we are using continuous wave systems. And this is something that you can investigate via the tutorial that I've provided for you to use if you wish to. So linear models in functional near-infrared spectroscopy, by definition, we are recovering a functional change from dynamic or temporal data. That means I can collect data on a subject at baseline or rest. So for a given source and detector and another source and detector, I can collect data. Then there will be some stimuli or some activation in tissue, and I will collect that data again. And now the aim is to recover changes in this optical data using this dynamic measurements. So the rate of change of absorption is given by the rate of change of data, and all I have to do is invert my model, either be a Lambert or other models, to recover these changes in attenuation. One step further about image reconstruction, because we will sort of see this from Adam later on, instead of looking at spectroscopy or point changes, we could do this for image reconstruction as well. And this is really an optimization or a minimization problem. And what we are saying is, given a set of data Y from a subject on the boundary, then what we want to do is we want to find a model whose absorption and scatter will match the data as best as possible. So we are minimizing the difference between modeled data and the measured data. And if we take this equation and we differentiate it with respect to absorption and scatter and set the derivative to 0, we are trying to minimize it, we end up with this update equation that will basically allow us to take a set of, measurements to recover a set of absorption and scatter that would give rise to that data in a tomographic manner. But when it comes to imaging, the problem is really difficult because unlike MRI, we don't have volumetric data. We have a finite set of measurements on the surface, typically in hundreds or thousands, to recover a spatially varying optical properties, typically in order of 500,000. So mathematically, this becomes very challenging, but still possible. But the question is, what model do we use to do our computational matching? And our typical model is a diffusion that literally says that given a source on the boundary, we have some changes due to absorption, we have some changes to diffusion, and that diffusion really is absorption and scatter, and depending on the modality, we either have a frequency variation or time variation as well. So conceptually, what it means is, given a domain, I can inject light at multiple sources, measure how much light comes out, and I will do that sequentially perhaps. And what you see on the measurement side is, again, typically what you will see in X-ray CT, what we call projection data. And if I was to use multiple boundary measurements, then I can push this back to my image reconstruction algorithm, and I can end up iteratively minimizing my problem. So I start with an initial guess, and as I iterate, I can get a fairly good recovery of spatial maps. So I'm very conscious of the delay that we had this morning. So I just want to go over our internal learning objectives. So now I hope that we have understood why we are using the infrared in imaging and its benefit that it has over other modalities. When we are using light within biological tissue, then we know that some light is being absorbed and scattered. And also there are different models that we can use to predict this light propagation in tissue, and that allows us to recover optical parameters either as spectroscopy or tomographically. One thing we haven't done is use a computational model near-fast to actually model data and to study some of these effects. So what I have done is I have provided 2 links here. So if you were just to go and look at Google Near-Faster or go on GitHub, you can download our GPU-enabled computational model called Near-Fast. And what I've also done is I've created you a MATLAB script, which you can find on this tiny URL. And what you will do is you will be able to run that MATLAB script with Near-Faster, and it will literally take you through the steps of how we can actually model data and look at the calculation of these optical properties given a set of dynamic measurements. And I think on that note, I will stop and let somebody else take over. Thank you.